Hello and welcome to this video on part 7 of our logarithm chapter. This lesson is entitled Logs Go Viral. In our last lesson, we introduced or reintroduced the constant e, which is about 2.71828. And as a reminder, to find e on your calculator, if you push the second and then the ln button on your graphing calculator, that will give you the letter e, allowing you to use an exponent with it at the same time. Now, when things are growing or decaying continuously, just like continuous compounding interest, E is going to be involved with that situation. And so if you have things that are growing continuously at every moment, we have one equation for that involving E. And then continuous decay, or where it's shrinking it continuously, is our equation on the right-hand side over there as well. So now, just like before in other exponential growth or decay problems, the A is what you're going to end up with at the end of time t, and so we can highlight that as well. P is the amount of stuff that we're starting with, like the amount of money we're starting with at time 0, and R is the rate of growth or decay. So just remember that when you're talking about R, that R is usually a percentage, and it's usually written as a decimal as well. And this can be used in a lot of different situations. We could use continuous growth or decay to talk about money, compounding interest, like we talked about yesterday. We could talk about populations of people. We could talk about radioactive decay. We could talk about animals or cells splitting as they are kind of growing continuously. So when we have this E as our growth rate, or involved with our growth rate for exponential growth or decay, well, the opposite of that is going to be something called a natural logarithm. And that is going to be a logarithm where the base is E instead of being base 10 or a 2 or any other regular number. And this sort of natural logarithm can be used to model lots of different situations, like same with E as well. And specifically, it could be talking about cells splitting where it's kind of happening really fast. So this lesson will be very apt with what we're going through in the world today with a pandemic around the world. And we're going to be kind of looking at a fictitious version of that. In this version, if you look at our bottom paragraph of our page here, us as the epidemiologists, we're going to be looking at a virus where the growth of the virus is continuous. You can see down at the bottom there. And it's growing at 3% per day. And we are starting out with 5 confirmed victims of the virus. And we're going to basically be saying that there's going to be 5 victims, and that is going to be where our day 0 is going to be happening. And so now we basically can work on our next page and starting to develop a function, table, and graph for this situation. So now if we are kind of thinking about this situation, we have a virus that's starting out with 5 victims, and we're going to be using exponential growth. So our general form of our equation is that right there. So just remember that P is going to be what we're starting with. We have base E, and then R is our rate of growth as a percent usually, which we know in this case is going to be 3%. And T is going to be, in this case, the number of days that have happened. So if we make an equation, we can actually make an equation pretty easily first. So we know that we're starting out with 5 victims, and our E is involved since this is continuous growth of our virus. And our 3%, 0.03, and then to the power of T. So think about if T was 0, where I had that filled in our table already, that would be 5 times e to the power of 0, or just 5 times 1. And so now if I wanted to fill out the rest of that table. So if I wanted to do 1, for instance, so if I get my calculator here, I'm going to be doing 5 and then second ln for my e value right there, and then 0.03 times 1. And so that basically goes up to 5.15. And then I could kind of keep doing this and filling in the rest of my table for the first 5 points after 0. So you can see that we have things kind of starting out slowly after the first couple days. And these would be all kind of parts that would kind of would make sense for exponential growth, that it starts slowly and then kind of picks up speed afterwards. And 2 more rows left. After 4 days, we'd be up to 5.63. And after 5 days, we'd be up to 5.81. So our graph, if we have 5 up here, is going to kind of go kind of slowly like that and kind of start to increase speed as it continues from its y-intercept of 0, 5. Now that we have our equation, we're going to look at day 30 and day 60. Both are fairly straightforward things to find. For day 30, it will be 5e 0.03 times 30. So now if I calculate that, 5e 0.03 times 30, well, that's 12.3. And since we're talking about people here, well, we probably would want to be rounding down. So that next person hasn't been infected. So we might be rounding down no matter what. So about 12 people are going to be infected after day 30. And then if we do the same exact thing for day 60, well, that would be about 30 people. So now if we are looking at day 30, we were at 12. And then if you double that amount to 60, we've more than doubled by that point up to 30. So we could figure out how we could get up to 50 victims, 50 people. So that's less than double from 30. So it's probably going to be less than 30 more days to get there. So it's going to be less than 90 days, which is a good way to kind of ballpark it at first, but not a great way to get to the exact answer right away. So what we're going to do here is use some solving equation skills. So if I want to figure out when it's going to be 50. So I have 5e 0.03 times some amount of time, so t. And that is going to be equal to 50. And so now if you are trying to solve this for t, so one way you can do this by graphing, and you could use Desmos or your graphing calculator to see when 50 would be equal to this left side of the equation. But we're going to do some solving equations instead. So if I divide both sides by 5, 5 divided by 5 is 1, 50 divided by 5 is 10. So I would have e to the power of 0.03 times t is equal to 10. So like we've done in class before, we're going to try to solve this for t. So if we're solving for an exponent and a power, we got to use a logarithm. So just like logarithms before, I'm going to rewrite this with my base. So I basically would be writing log base e. And then my exponent is always the answer. So equals 0.03t. And then my input is left over as 10. So this is log base e. The log button in our calculator does base 10. But the natural log is what is base e. So if we kind of go up here to write some notes down. So if you have something that is log base e of x, that is the same thing as basically writing ln of x. This right here is known as a natural logarithm. And it's just base e, so we're talking about continuous growth or decay, logarithms, exponential form, and that's what we are using natural log for. It's ln instead of nl because the original was Latin, and it would be, the words were in a different order, so it's not something we need to worry too much about, and that's just why that is reversed there, if you were wondering. So when you have a base e equation, we're going to be using natural log to solve that, and so we can use our calculator from here. So what really is going to be happening in our problem down here is that we're going to be basically writing that as ln of 10, our natural log of 10, would equal 0.03t. So then I would just be dividing both sides by 0.03. So natural log of 10 divided by 0.03 equals t. So grabbing our calculator. So first things first, if I am talking about natural log, so we just look for find the ln button on your calculator. So right there, ln. So if I push the ln button, so if I did say ln of 10, that means that we'd have e to the power of 2.3 equals 10. So we can check that. E to that power equals 10. So what we really wanted to do in this problem, if you look back at our work, is that we wanted to do natural log of 10 divided by 0.03. So natural log of 10 divided by 0.03, that equals 76.75. So if we rounded down to 76, we'd be short of 50 victims. If you round it up, we'd be past it. So, I mean, we could basically just say round to the nearest amount of days. So about 77 days for that. And that's how we're going to be using natural log to solve base E exponential equations, which is a big part of this whole chapter in general. Moving on. So now if we are looking at number 4, will the number of days that it will take for a virus to claim 100 victims be double the number of days it took to claim 50 victims? Why or why not? So if we look back at some of our previous answers to questions, we figured out that we had 12 victims after day 30. If we double our input to 60, we more than doubled our people that were affected by this virus. So that just shows that, and with exponential in general, we don't have, if you double your x, you're not going to be doubling your y. It's going to be even more than double your y if you have exponential growth. And that is the case for all exponential functions. Linear functions are the ones where if you double your input, you are also going to be doubling your output. So if I go back to the question we were asked, will the number of days it will take for the virus to claim 100 victims be double the number of days it took to claim 50 victims? Well, the answer is no. No. It will take less than double the days for 100 victims. All right, so now let's actually find what it would take for 100 victims. So our equation was 5e to the power of 0.03t, and now we're going to see when it's going to equal 100. So first step, divide by 5. Now we have 0.03t equal to 20. So then if I rearrange it into a logarithm, so now we have log base e of 20 equals 0.03t. But remember, we're using natural log here, so it would be natural log of 20 equal to 0.03t. And then we'd just be dividing both sides by that 0.03. So our answer would be the natural log of 20 divided by 0.03. 0.03. And that is going to be giving us the amount of days we want. So natural log of 20 divided by 0.03 equals 99.9 days, or about 100 days. So if we look back for 50 victims, if we are 50 victims, that took 77 days. So 77 days for 50 victims. If we now look at our work here, well, if it was 77 days for 50 victims, for 100 victims, well, that was only 100 days. So that was only 23 days more for double the amount of victims. And so now, last problem of this, on what day will there be 150 victims? We'll just be solving 5e 0.03t equal to 150. So dividing by 5, we get e to the 0.03t equal to 30. And now we can just rearrange now that we know what we're doing. So now we're going to do natural log of 30. It's going to be equal to 0.03t. And then we're just dividing by the same 0.03 that we did in the last problem. And we get an answer, natural log of 30 divided by 0.03. That's about 113 days. And that would be 150 victims. So 150 victims, 113 days later. Okay. So now we are looking at a slightly different situation. So now we have received a mysterious illness that seems to turn infected humans into mindless zombies. Well, that's not very good. Since the hungry zombies prey upon innocent people, the outbreak grows continuously at a rate of 12% per day. So we're seeing the words grow continuously and also 12%, and we're seeing starting with 80 people. Okay. So after 5 days, in order to figure that out, we got to make our equation first. So our number of people is 80 that we're starting with, and our rate is 12%, so 0.12 times t, and that is the equation we'll use, meaning that we can do 80 times e to the power of 0.12 times 5, and that will be after 5 days. So grabbing our calculator, 80 e to the 0.12 times 5. So we got 145.77. So that means we got about 145 zombies in our midst. Never a good thing to have zombies in our midst. So now the problem below it, 8, is asking about 3.7 million zombies, which is about the population of Los Angeles, which would be very devastating to have that many zombies walking around anywhere. So we're going to be solving 80 e to the 0.12t equal to 3.7 million. So the first thing we need to do is divide both sides by 80. So I'm going to do 3.7 million divided by 80 first. So you get 46,250. So I got that as my E right there. And now we need to rearrange this into a natural logarithm. So the natural log of 46,250 equals 0.12t. And now we're just going to divide by 0.12. So natural log of 46,250 divided by 0.12 equals t. Putting that in our calculator, we get the natural log of 46,250 divided by 0.12. That is an answer of 89.5. And this is days. We can say that is just days. So about 89 and a half days to get to 3.7 million, which sounds about right for based on the zombie shows that I personally have seen, which is very fast. So that's another natural log solving problem where we were able to get an equation for it. Moving to our last page of our classwork and video. So this number 9 is a little bit different of a problem. It's asking about the rate. So at what rate? So we're trying to find the R value. We don't know R value in this particular problem. And we want to see 190,000 people. So that's what it's going to end up being equal to. And we know that it's 20 days. So remember that our equation was 80e.12 t equals y. So we know the y is 190,000 people. And we know that our days is 20. So the 20 is going to be our t value. And so we don't know the r. So it's going to be r times 20. So we're going to be doing some similar stuff, but just a couple things changed as we kind of look at this. So now if we divided by 80 on both sides, 190,000 divided by 80 is 2,375. So it'd be like e to the 20 times our unknown r for rate equal to 2,375. Now we can rearrange it into a natural log. So the natural log of 2,375 equals 20 r. And now we're just dividing by 20 instead. So we'd be doing in our calculator the natural log of 2,375 divided by the 20 days we know about, and we get 0.3886. 0.3886 for R. So this is the rate, remember? So this is percentages. So this as a percent would be 38.86% growth rate, which would be much faster because our growth rate of our zombie situation before was only 12%. So 38% is more than 3 times faster of a growth rate, which would be much more devastating to your Los Angeles population and maybe kind of overrun with zombies. All right, so now we are at our final 3 parts of our classwork. So in this kind of more far-fetched scenario, we're saying that our zombies produce goo that is radioactive and decays continuously. So we have continuous decay with a half-life of 3 years. That's one more danger of having zombies around. Half-life tells us that after 3 years, only half of the amount of goo we started with is remaining. So basically what we have to do is we're trying to figure out if we start with 10 pounds, how much are we remaining after 5 years? So remember our P times e to the negative RT was our continuous decay function. Now the approach to this problem is going to be a little bit different because we have to figure out some things before getting to 10, 11, and 12. So what's going to happen, we're going to split this number 10 in half and kind of come back to figuring out when it's going to be 10 pounds of this zombie goo. So it doesn't tell us exactly how much we're starting with, but it does say that we have a half-life of 3 years, which means that after 3 years, we're half of what we're started with. So whatever our P is right there of our exponential decay, continuously decay formula there, So we're going to end up with half of whatever p is. And we know that that is going to be after 3 years. So our t is 3. We don't know r, and we don't know p, but we do know that we're going to end up with half of p. So the first thing we could do is cross out p and p. So we just basically have e to the negative r times 3 equal to 1/2. Now, from here, I basically can rewrite my problem first. 1/2 equals to negative 3r. And then rewrite as a natural logarithm. So natural log of 1/2 equal to negative 3r. And then divide both sides by negative 3. So I would have natural log of 1/2 over negative 3. And that is going to be equal to my r value. And that equals 0.23. So it's going to be a 23% change. But we're going to use this 0.23 number. So going back to our problem, so if we start with 10, well, now we know that our rate is 0.23, so negative 0.23 t. And we're going to basically figure out when t is 5. So 10 times e to the negative 0.23 times 5 years. So we put that into our calculator here. So now we have second ln for our e to the negative 0.23 times 5. And then we got to multiply that by 10. So we get 3.16, so 3.17. So after 5 years, we got 3.17 pounds of zombie goo using our half-life information and our continuous decay information. So almost done. So 11, how long will it take for the amount of zombie goo to decay to an amount less than 0.5? So basically what it means is we have 0.5 is greater than our equation, 10e negative 0.23 t, like so. Now we can divide by 10 first. So now we would have 0.05 is greater than e to the negative 0.23 t. And now we can rearrange into a natural logarithm. So now we have the natural log of 0.05, and then we're trying to see when it's going to be equal to negative 0.23 t. So now I'm going to grab my calculator, and I need to divide first. So natural log of 0.05, and that is going to be divided by negative 0.23 for our t value. And so now if I divide those in my calculator, so I'm going to do the natural log of 0.05 divided by negative 0.23. So that answer ends up being about 13.02. And that was, I believe, years. So a little over 13 years later for it to be less than 1/2 pound. So if I try to solve this 0, so when no zombie goo left, that just means that 0 would equal to 10e negative 0.23 t. Trying to figure how many years it would be until 0. So divide by 10 on both sides, well, we just got 0, e to the negative 0.23 t. And if I rearrange that, I would have the natural log of 0 equal to negative 0.23 t. So it basically would mean that I have e, which remember is about 2.7-ish, raised to a power and getting me 0. Which, if you remember about logarithms, that's not actually possible. You can't raise a number, any kind of rational number like or irrational number like e, or any rational number like 2.5, for instance. If you raise it to positive exponents, it's going to get bigger. If you raise it to the power of 0, well, that just equals 1. If you raise it to negative exponents, well, that is going to be giving us smaller numbers, like fractions, small decimals. So there's actually no way for this to be true. So that is not a true statement. So there is no way to get to 0, which is actually something to think about before we end the video here. And you have radioactive decay and half-lives of those. Basically, it means by this model that we've been using, that radioactivity is never really going to be gone, even though kind of half of it will be gone after a certain amount of years and there'll be almost none left. It'll basically never reach a point where it's at 0, at least by the model we've used so far. And that concludes this lesson on solving exponential equations, especially continuous growth equations with e involved, and using natural logarithms. Thank you for watching.